scan there, and then for the Cosmo RS, let's first use the Cosmo RS cyclohexane. First do the cyclohexane calculation, and we can use the optimized geometry. Acetamide gas dot xyz. So this Cosmo RS cyclohexane is the line which will do the Cosmo RS calculation. Let's acetamide dot INP. So it says that it cannot find the file. There has to be a space after this. Yes, this was the problem. So this calculations actually will take some time because it's not a single calculation, it actually contains multiple calculation, and the final output will be printed in the acetamide.cyc.out. So each of these output file, first it's doing a calculation at the gas phase, then it will do the solute calculation in the PCM phase. So, now the calculation is done. Let us see the output file. So, it says open Cosmos calculation. So, these are the individual parameters, and in the solvent data what is important is the free energy change of solvation. Now, this is we have done it for the cyclohexane. We have to do the same thing for the gas, for the water. So, I will redo the calculation as water. So, this is the solute in gas phase, the second one will be solute in CPCM, and the third one will be solvent in CPCM. Remember, we have done the optimization in the gas phase. So, the only difference between these two is the change in the free energy of solvation, that is this one. So, if I use a calculator, or maybe I should use the Excel sheet, a new one. So, this is in water. This is in cyclohexane. And if I take the difference between the two, because I am going if I take the difference between the two, this is how the difference is, and remember experimental values is kilojoule per mole. So, the conversion is 2625 approximately. So, it has come around 26. Oh, the experimental value is given in kilocalorie, I was mistaken. So, at case the conversion factor is 627.5. minus 6.30, and the experimental value is 6.4 kilocalorie per mole. What I am getting is minus 6.340 kilocalorie per mole. So, the results are in pretty good agreement with the experiment. Now, your homework problem will be calculation of the free energy of acetic acid, now going from chloroform to water using the Cosmo RS module. So, up to now we have talked about the solvation correction to the ground state. In week 10 we have described about excited state calculation in the gas phase. Now, let us see how the excited state calculations are actually influenced by solvation. So, the excited state calculation can be done by both in a linear response and state specific way. In ORCA, the TDDFT and the CIS calculations are generally treated by the linear response CPCM as developed by Kami and Tomasi, and is implemented both for energy and gradients of excited state, and this is what is turned on by default whenever CPCM calculation is also requested for the ground state. So, the major change what happens is that with the addition to the CIS or TDDFT term, there is this additional G term which actually comes due to the solvation correction, which is defined like this. So, you can do the CPCM calculation by just for the excited state, the linear response CPCM, just by using the keyword CPCM water. So, if you give it for the excited state, it will also actually calculate the correction linear response CPCM correction to the excited state also. So, here you see the changes comes due to the two facts. First of all, because I am adding the CPCM thing, I am actually changing my Hartree-Fock coefficient, because remember the del G will be solved now variationally instead of electronic energy, and additionally the excited states are corrected using the linear response PCM corrections. So, let us do this calculation. So, let us make the input file. First, let us do the gas phase calculation. Maybe it would be interesting to see the molecular orbitals. So, let me write large print and I want to be fast, so I am writing Rij cos x. Okay, I should have written RHF also, but if I have not given anything, then it will automatically do an RHF only. Let's open the MOBIX terminal. Okay, we have not ended the output file with the star. Now let us see the output file. So, the dominant transition is from 7 to 8, that is Homo to Lubo transition, and we can actually try to open it using ChemCraft to see the orbital picture. The excitation energy is 4.626. So, render molecular orbital, we are just interested in Homo and Lumo. So, this is NP to pi star kind of an excitation. We have seen before also. Now, let us run the same calculation in water. So, it was 4.63 I believe, now it has become 4.85, and of course, the nature of the calculation it will still remain HOMO to LUMO. We can cross check it. The nature I render the orbital. So, the nature of the orbitals remains same. But actually the energy increases by around 0.2 electron volt. So, that is the effect of the solvation. In some of the cases, the nature of the excited state might also change due to the presence of the solvation. Remember, however, if you are dealing with a situation where there is a charge transfer from the solute to the solvent, that kind of thing cannot be treated by an implicit solvation model.